At 5 o'clock today, your summary is due, and the story is up until last Wednesday. There were just a few questions on that. I think most people know that the last two lectures are for fun, so we'll make it a little bit more that way. It's a little bit of a departure from materials processing, and the reason is I've emphasized so much the the grain, the dendrites, and all sorts of things that relate more to mechanical property, when in reality, when you select materials, you also have to take into account the environment and how you're going to protect it. And we did the first step towards that when we talked about galvanizing last time. And this is the case of a hot dip where the steel structures, they all welded, almost ready to go. It's done a lot for bridges nowadays. Even if they paint the bridge, a lot of times there's a galvanizing underneath of it for steel bridges. The other way to galvanize is galvanizing sheets. Electrogalvanizing, it typically gives you much less thickness. So we'll talk more about what happens during corrosion, and from previous years I find that that's where I see a lot of surprise faces, and that's always good. It means that you're learning something. You have a lot of causes for what people call corrosion. So this is just a summary table. Traditionally, it may have changed a little bit over the years. You have general corrosion, so that's thickness loss. Stress corrosion, I've talked a little bit about it when we had the big chain. The mooring chain was a case of stress corrosion. So it's not that you had a significant reduction in the thickness of the chain. It's just that there's this crack, environmental crack, that started and propagated almost halfway through the section. You have pitting, and pitting is most typical with aluminum and stainless steel and copper, because they have this natural oxide that you can lose through the corrosion process, through the environment. So you start from having kind of a nice coating where everything is protected, and then when you lose it somewhere, it tends to localize. So pitting is a localized corrosion, like drilling a hole. And sometimes it will look like drilling a hole. So these are just a little bit on how it's different in terms of the material. When you have the uniform corrosion, it still leads to a roughness on the surface, and this is something that we'll talk about, why are we developing a roughness. The case of galvanic or crevice corrosion here is where you have two different metals or two different conditions. So in one case, on the crevice corrosion, you have a lot of oxygen, you're exposed to the environment, and under the crevice, you have very low oxygen. So it leads to this different reaction taking place here. So it's kind of a battery effect, those two cases of galvanic and crevice corrosion. But what you'll see today is even uniform corrosion still happens through a battery effect. So this is where it all comes together, hopefully nicely. Now, when you are starting to hit very specific portion of the microstructure, it's a little bit of a galvanic effect. So those two phases have a different potential, and you can start and preferentially corrode between the grains or in different phases of the microstructure. So there's a number of brass alloy, for example, that have this two-phase structure. It's a different chemistry. So at the small scale, you have this effect of one is wanting to corrode preferentially as opposed to the other. So it goes on a lot more quickly. So it really is an overview. The pitting, we talked about it, it's forming holes essentially, and a lot of times that's related to having a protective oxide on the surface. The erosion, cavitation, fretting, these are all very different. I don't know why they're in the same schematic, but in the case of erosion, you do have flow going on. It's a liquid flow. And what happens is lose this stability against of the protective film. So this will happen in copper pipes, for example, where you have a little bit too much flow at bends or elbows, and then you lose the stability of the film, and all of a sudden you lose the thickness. So the same environment, just different conditions, so such that you lose the surface protective layer. Cavitation is typically when you start forming these air bubbles, so it also kind of is a flow mechanism where you attack the protective film preferentially. You come and you have a high pressure followed by a low pressure, and you generate gas, and that explodes on the surface. So it's destructive to the protective film. Fretting is very different in my point of view, in the sense that at this point it's just two solids, two pieces touching over a very, very small amount. So you mechanically separate the and detach your protective layer repeatedly. So you take it away, it reforms, you take it away, it reforms, and then you have a section loss, you have essentially also a preferential site to start cracks. That's what happened with fretting. So I guess one way to think of it, this entire first row there, they're all related to the stability of a protective film. And then the environmental cracking, if it's stress corrosion, it's just a constant load. And then this is something we've talked about, where if you have enough force applied, then your rate of growth of that crack is very constant. And what really needs to happen is the diffusion of the reaction product to the tip of the crack. So as long as you can supply these three cracks with the same reactant, they all continue to go, even though normally this one is a little bit protected by the other, so it definitely has less stress intensity on it, and so you'll expect it to stop, but it won't a lot of time. Eventually they may stop. On the corrosion fatigue, so this case you have a cyclic load, and that's typically harder to see after the fact. You almost need to know the loading conditions to identify corrosion fatigue. Hydrogen-induced cracking is a little different. It has to speak to what is the potential at the tip of the crack. So if your potential is becoming a cathode, then you a little bit in this situation where you try to generate hydrogen. You corrode somewhere and you produce the hydrogen at the tip of the crack, and it's not acting like a solvent or lubricant, but it is penetrating in the material and enabling certain modes of deformation and surface separation that you wouldn't have otherwise. I think it makes sense if you have these small atoms that all of a sudden it's easier to separate the surface. So that has its own characteristics, and sometimes just the fracture surface is going to tell you what you have. Sometimes you also want to combine with information that you do know about the environment and the usage condition. So let's go back to a little bit more simple stuff. So this is along the Esplanade. There's on Stowe Drive. There's one lane when you go eastbound that you go through a tunnel, and we worked there for a while looking at essentially some cracking they had between beams. You have the main beams that span across the lanes, and then they have these longitudinal beams that were supposed to act as diaphragms. So you help, I may as well lay it out. So you have the lane, let's say the lanes are this way. So you have this big beam going across here, and you have another one and another one. And the issue is it's traffic on the upper level for the westbound side. So if the load is concentrated on one of those beams, you can get too much deflection. So what they do is they essentially put braces. So they have these beams going between the two big beams to have them act together. So if there is load applied here, it's actually applied to all three beams. So but you could probably see when you're talking about hundreds of feet of tunnel, that with temperature changes, now you're trying to contract and expand this way, and that's easy because you have the supports over the walls of the tunnel. But this way, these beams want to contract and expand, but it's held here, so there's a little bit of a side forces involved. And it wasn't stress cracking, but what we're looking at here is the intersection over there. This one wasn't cracked, so I'm bringing it up mostly for the effect on corrosion. So again, it's just the same material over the entire sheet, and it's rough. And the reason is you always end up having anodes and cathode, even if it's we call it uniform corrosion. So by the time that you form a reaction and you start removing material right here, what happens is you have the flow of electron to oppose to that, and you generate the hydrogen, or you have reduction of water depending on your environment. So after a while, you have a certain buildup where over at the cathode, the environment has changed, and then normally it will want to flip right over. So what used to be the anode and the cathodes is going to completely change, and you have the reverse reaction, but it doesn't happen perfectly. So that's why eventually you have a certain roughness, but the roughness shows you a little bit the landscape of this reaction going back and forth. Anode, cathode, because it's the same material. There is no real big difference other than the geometry, the environment that it's subjected to nearby. If this is happening in water, a lot of time it's the supply of oxygen that is the limiting factor. So you have a certain corrosion rate, 4,000 of an inch per year. If you submerge in water, it's just the time for the oxygen to come. So you can think of this, that when you use the oxygen at a certain location, now you don't have as much of it after a while, so that's another reason for switching to another site for the corrosion. So it's I guess all that complexity of having a cathode and an anode happens on the same surface. This is from that tunnel, and you can see it's about almost 10 millimeters in thickness here. And these beams were about 3/4, so you could get very worried when you see these. They were at expansion joints, so it's a place that you have more penetration from the upper levels potentially of moisture and salt from the winter. The point I want to make is it is not the steel. By the weight of it, it doesn't weigh the weight of the steel, so it is the corrosion product that built up and it's expanded. So it's about 3 to 4 times bigger in volume than the original steel that was used to make it. So it's not too bad for the application. Yes? Oh, I thought there was a question. What happens when you have corrosion over time is a little bit more complex. So this is a tank that was in the ground for 60, 70 years. So when we're talking about the surface of the beam right here, it's rough. It really was all exposed to the same environment. So if you go and measure the thickness at these different locations, it is still very similar. And the main reason, it's the same environment. You transfer from anode to cathode all the time, and then eventually you just lose thickness in relatively homogeneous matter, and that's what happens a lot in atmospheric corrosion. In the ground, you have the additional effect of the soil. So if the soil in one area is very impermeable, But the soil in another area has different condition. You end up a little bit like in a crevice condition that was on the schematic at the beginning, where now permanently you're going to have the anode at one location and the cathode at another location. So this specific tank is regular steel, so it doesn't really have the protective film or anything like that. The oxide is not stable, but the entire weight of it was very similar to what it was 80 years ago, but it had holes. So the reason for the holes is the difference in the condition of the corrosion. So if it was embedded in sand, for example, you wouldn't have this because everything around it would be the same all the time, or nearly the same. So it just speaks to understanding these factors when you want to use something. So let's say we want to build a steel levee, for example. We want to make sure that the moisture from the ocean doesn't go beyond a certain point. So we're going to drive these walls into the ground. It goes for miles, and it's going to stop or control the inflow and outflow of groundwater. That's done quite a bit. So if let's say you want to do that, then you need to know what kind of soil you're driving the steel in to have a sense as to the type of corrosion you're looking at. And your problem is slightly different, because if you're looking to put a reduction in the flow, if you're not necessarily trying to completely isolate one side of the ground with the other, you may be willing to live with some local corrosion like this. You have some permeability. In 40 years, maybe you'll put some pumps, or you're going to add something else to compensate for this loss. So it just speaks to kind of what your objective is. If it's a pile so these big beams of steel, you lower them to the rock to build large buildings. Maybe on these cases, you really want to make sure you don't have buckling after a while. So you don't want these sections to lose their capacity. So at that point, you have a lot of options. You can go and galvanize it. That's going to buy you, 50, 60 years, something of that order, even if it's underground. So a lot of times that would be sufficient, but if you wanted a thing further than that, we talked about cathodic protection. So you put a current onto the structure. So just in terms of what happens with steel, this is a study put together we were working around a power plant, and they wanted to decide on a galvanizing or other means of protection for all their applications. And the truth is, it is very, very different. The type of corrosion rate you get in dry air is very, very small. It's actually, these are recommended value. These are not all actual values. So when you get into a submerged condition is where here you have a value of about 4 mils per year that you lose, and it's very constant. If you're in the ground, it's also the same amount. So a lot of times you need to have very large structures if you want to be able to live with losing thickness over time. So for a lot of what we build for transportation, for example, we don't really want to allow a lot of section loss. And one reason is it's hard to know where it's going to happen, and then it adds weight in the first place. If it's a building, then generally you'll have an allowance, but you can start to see that the life of the structure makes a big difference. So if we're looking at, let's say we put something in the ground in the water for 10 years, we'll lose 40 mils. So just less than a 1/16 of an inch. It's not a whole lot at that point. But then if you start talking about 50 years, now it's becoming significant. So it's all a question of time whether you're willing to live with the thickness reduction or not. You want to protect it. A lot of times we'll use the environment. So when we protect steel reinforcement in concrete, all we do is we use the environment to put the steel at a pH where it has a stable oxide to protect it. So you stop the corrosion reaction. It will work very well if that's this region here, pH 10 to 12, as long as you don't have a degradation of the concrete. So if the concrete starts to crack, even if it's a little amount, and now you have water penetration and you lose this high pH where the rebar is, then now it starts to corrode and spall. So it's a major issue for the use of steel as a reinforcement, because if you always end up with some degradation of the concrete if you have cycles, especially thermal cycles and history and different loading, and it's a big structure. So when you do, then they do have a number of alternatives now. They'll put some epoxy on the rebars to protect them. They can galvanize them, or just do like we traditionally do, deal with it when it's starting to fail and repair it, because it's all long term and you can't spend twice the money up front necessarily for a structure. Say it's going to last 60 years as opposed to 25 years, for example. One thing that they'll do for a certain structure is, instead of having the steel everywhere in the bar, so let's say you have a deck, a concrete deck, and you have the rebar a little bit everywhere in it, whether it's just put in, cast in, or it's pre-cast, pre-tension, it's the same effect. But on certain big arches, what they'll do is, let's say this is the main concrete structure, so they'll have a little area here where they'll put the steel reinforcement. So this section goes this way, and the idea with this is you put a lot of tension in the steel that's located in that cavity, and you attach it at each end when it's all ready to go, and it puts the entire concrete in compression. One advantage of doing it this way is you can more easily keep track of that environment. You can decide to put another concrete, so they'll put a grout, for example, that is very low strength but has more stability. So you work your environment over time, that you're not going to have this change in the pH, for example, and the exposure to the environment. Now, all of this is done either, this typically done in the shop. This has to be done on site. So there's a lot of implication, and there's more work involved, and a lot of times you have to seal each end of this and make sure that it's okay. You can go back. So here, one advantage is you can go back and find out if you had failures. You can run a test and determine, are these all good still? So there's more inspection that can be done. But it's all about adjusting the environment to eliminate the corrosion. With aluminum, we're blessed because in a typical atmospheric condition, you have a stable oxide on the surface. So that is from pH approximately 3 to 9, you have this oxide forming that is relatively stable. Now, we have to take that into account, because pH 3 to 9 doesn't cover all the application. If you use an acid cleaner for a piece of aluminum, then you can get into trouble because you lose that protective oxide. If you embed aluminum in concrete, you can also lose the stable layer and have a section loss. And so the stability, the thermodynamic stability of the film helps us understand limitations. So we don't want to use, even if it's lighter, we don't want to use aluminum as a reinforcement in concrete. It doesn't help it, it can actually make it worse. In acidic environment, that's where the pitting starts to take place. So you can think of this that, let's say we're talking about aluminum for an aircraft. Okay, the pH, you know, it's not too far from neutral, even if you're on the coast, but then you start thinking, okay, well, maybe I'll have a little salt deposit on the surface of the aluminum. So locally, I'm going to change the conditions. And that's where the pitting really starts in a lot of other conditions, just by locally changing it and having enough potential to break the natural oxide. So it's unfortunate. Can't make everything work. So the goal today is just have a little bit of awareness of what's happening. So the anode and the cathode, I don't want to go too crazy with it. I think you understand that if you put a sacrificial material, so when we talk about galvanizing, is where the zinc here acts as the anode, and you start forming the ions. So the only way a galvanizing is effective is if it's able to share the same electrolyte as the part and also be electrically connected. So you really have those two conditions. It's the same for having a galvanic reaction when you have two different materials. They have to be touching, but that's not enough. They have to also be submerged or sharing a very moist environment or an environment that really they electrically connected and connected through the ion path as well. So this is a little bit out of place, to tell you the truth, but we talked about two things so far. We talked about hot dipping zinc to create that surface layer. We've talked a little bit about thermal spray last time, where you can create the same zinc layer by spraying. You just need a lot of surface preparation, and you need to spend the time, the effort it takes. You guys saw the torch. It's not an easy process. It's more complicated than painting. You can use a paint. So in this case here, you see there's a binder, there's some particles, and they have different grades, and it's a whole science in itself to have a paint that you apply with a brush that will have enough zinc in it to connect electrically with the surface, or be electrically connected and be porous enough to get to the surface and still protect. So it's a very interesting application, because at that point you don't need as much surface preparation. So it's not as expensive of a process. It does have limitations, of course. The galvanizing, so of the sheet metals, here they just really do it very quickly. Or you can electroplate. So let's say you go to the hardware store and you see a fastener that just doesn't look like bare steel. A lot of times it's just going to be electroplated. And the reason is it looks good. They can sell it to you. It's not going to rust until you put it on. And then a year later, so that's the type of time frame you're looking at, maybe a year or a couple of years, that it starts to corrode. So you've lost this electro plating of the zinc. And the one reason for doing it's not just cost, is when you put a very small amount, all the threads and everything still work very nicely. When you're looking at doing a much thicker coating, like the hot dip galvanizing, sometimes they have to oversize the nut so you can still work the bolts together. So there's cost, but there's also, you know, how precise your threaded connection needs to be in terms of hardware. It used to be that, you know, they'll have a lot of screws that will be made this way for the same reason, where the head of the screw is harder to drive if it's been really galvanized with a thick layer. But there's been some changes with the building code if you're using pressure treated wood, for example, where now you have to use the hot dip galvanized, because you just don't have enough life here if you're talking about, you know, 10 plus years of service. It becomes a problem for, let's say, electrical appliances that are put in tunnels or bridges. So let's say you have a light system that would normally work fine, but now it's exposed to more humidity. It's outdoor and a little bit of a salt spray, essentially, from service. So now all of a sudden what used to be okay for sheet galvanizing doesn't last long enough, and they have to do an early replacement, and nobody's happy. So it is just this one idea that depending, it's good to understand the process of sacrificial protection, but then to determine how much you need for your application is, you can't assume that if it's good enough for somebody else, it's going to be good enough for you. This is an example of exactly just that, taking the sheet galvanizing and putting it in these walls for a very special museum in Denver, Denver Art Museum. So they had a special siding that they were putting on that they needed to drive a lot of screws in it. So you have the sheet of steel here. You see that there's a fastener that went through it. And what we're looking at is this layer, that's the galvanizing, and you don't have the galvanizing next to the hole after just 3 years of service. So what happens is it's a moist environment. It's not completely submerged. And when that's the case, there's only so far from the hole. Let's say the hole ends here. You can go maybe up to about here, where you can consume the galvanizing. If you're further away, what you have to think about, it's a little bit like a drop of water. A drop of water is only so big. So if you're talking about moisture, there's a distance, if you go beyond which you can't grab that extra sacrificial material to protect the hole. So we were getting into this regime where most of the holes were consumed in terms of the galvanizing up to about the size of the hole. So up to here, there really wasn't any galvanizing left. It was just the byproduct that you see there. And the next step was normal thickness loss. So if you want to estimate the life of the assembly that was put on just a couple of years ago, you have to think about the thickness of that sheet here where it's threaded and see how much time it's going to take to lose all of it. Is it a worst case scenario? Maybe sometimes, because it gets confined. Maybe it's actually going to be faster because you have a sacrificial process. But I think the main point is, instead of being a relatively dry environment like they have normally when they use these things, it was moist most of the year, and therefore something that would take, let's say, 25 years to start taking place. They had it going on just after 3 years. They had other issues. This is not the only thing they have, but I think it points to a couple things. Is if you don't have that moisture shared, then you don't have the protection. Like if you have a pump that's running, it's very, very different than a pump that's stagnant. So if a pump that's stagnant, you can all have that ionic connection, and it causes more corrosion. So a pump that's not being used, that has different materials built into it, is going to corrode a lot faster than if it does have use and circulation that's preventing all these interactions from taking place. So other ways to protect other than galvanizing is you have the coating. So in the case of the tunnel, it didn't quite work in this area. So what happens a lot on coatings is they do have a different expansion. They're affected by moisture. They can't hold back all the moisture. So when the moisture penetrates, let's say you have, that's important about steel, and we'll make the difference with stainless steel. So let's say what we have is steel, and you put a coating on it. What happens over time, if that coating is not super impermeable, is you do get the moisture to penetrate until the interface, and then you start your normal reaction. You have, of course, the oxygen. It's just smaller. So you start corroding here, and it palls, just like it did here. So two ways around it. One is you say, well, I'm also going to galvanize this steel, so when the moisture comes in, all it's going to do is just have a low reaction with the zinc. So that works to the extent that you can attach the zinc layer correctly to this steel, and that's typically done. So on the hot dipping, it's very rare. You don't have corrosion. It's a problem with the zinc-rich paint, where you try to get as much zinc to contact, but it's in a binder. So there's going to be a lot of areas where there's a binder that's separating your particles that you're trying to put on. But probably the main point, if you're looking at more than a paint, if you're really serious about putting an organic coating on steel, is your first criteria is a coating that's not going to allow the oxygen to penetrate well. And those tend to be the hard epoxy or other relatively dense coatings that are hard to keep the adhesion with the steel with. So if you want to say, I'm going to put a coating on this and it's not going to corrode in, say, 15 years in water, you're looking at those specialized hard coatings that are going to require you to put your roughness on the first place to get a mechanical adhesion with the steel at the same time. So you have to do a little bit like you do with the hot dip galvanizing. You sandblast the surface, make sure it's dry, then you put your coating on, you let it dry long enough, and then you're looking into your long-term life. So it's used for ships, for example, or any very special structures. So it's two aspects. You need to work the adhesion typically on the hard coatings just because of how they're gonna have a stress there at the interface when they cool. They're not very compliant. So as long as you fulfill that need, then you do have your oxygen protection. You can put something that's very compliant on the surface, the paint, but is not really going to protect against moisture penetration on the long run. So it's hard to win on everything. That's just an example of, I guess, a more complex coating where they have the steel, they have the primer, and then they put this zinc coating. So zinc paint. We couldn't verify for sure that the primer was going to be effective here. I think that was a mistake, because if you have your sacrificial element so far from the steel surface, you need the primer to be conductive, and you need the ions to be circulating through all the way from the primer to the other interface. So this was probably a mistake where they should have put the zinc-rich layer straight on the steel, and in this case, let go of the primer. The top coat here, that's typically works. You can encapsulate against the environment, not get the moisture to come in as early. And for appearance also, it's done in a lot of situations. This is something that when we talk about large utilities, pipings, and things that are in the ground, You can't access them after the fact, so you have these locations to control the sacrificial anode. So let's say I put some magnesium anode somewhere in the ground, I run the wire to this port, and then I can also connect it to the steel structure I'm trying to protect, so I can go back and verify if my system's working after a while. And then if it's not, then that's a little bit of a challenge to go and put some more anodes and all that. So it's not perfect, but when talking about large structures and you're trying to monitor them and you have the cathodic protection, that's a way to do it. Galvanic corrosion. So the Liberty Tower is a good example where they needed this special appearance of the cast iron, and even though it did take 10 years or so to build, 10, 15 years, they were still in a rush. This was quite of a process to cast all that structure in. So one thing they did is they were trying to insulate and not have too much corrosion of the internal components, but over time there is moisture, and to the extent that they have a wrought iron armature, so this steel structure is held by wrought iron, you'll have a little bit of damage to that wrought iron because it's contacting directly. So the only way you could have avoided this situation here is by putting a complete dielectric insulation between the two of them, so not allowing them to be electrically connected. But they either didn't know about it or they didn't mind. It was going to be good for 100 years anyway, so that's pretty good. But it is a process that's going on all the time. So you have the copper that is resisting the environment. It is corroding, and it's transferring that corrosion action to the steel, even if the steel or the iron, the wrought iron, is not exposed to the environment. If it's moist enough and they're in contact, they do share locally the electrolyte. One thing to think about when we talk about galvanic couples and you try to assemble something is the smallest piece is what you always want to be the more noble material. So it's not a good idea to use steel bolts to connect these pieces of copper, and that's not a mistake they did. They were using copper rivets, even if they don't have the same strength, they don't have the same characteristics, because you don't want that small element to be the one that's corroding the most. So the ideal scenario here would be this wrought iron armature being, in surface a lot bigger than the copper surface, but it's not the case. So that's why they do have the local corrosion, and it's affecting a little bit how the joint can contract and expand with corrosion products building up in the interface. So a lot of times you'd like to think we can completely avoid these different materials being combined, but most of the time we don't. If we think about not just structural application, but plumbing, in plumbing you have a lot of different systems coming together. And again, the one clean way to do this is this dielectric joint. So let's say I come and I have two flanges coming together. I can put the dielectric here, and if I have bolts, what it means is I also need to put a sleeve here. So there's a dielectric sleeve. This is all dielectric, and then a dielectric washer. It's the only way, if I'm trying to connect material A to B, that I can do it without having a problem. And they sell those kits for different sizes, so it can be done, but you have to be fairly proactive, because it's not out there. It doesn't come with the fasteners. It will take care of making sure that the fastener, the bolt that you use, doesn't act as the the element to do the electrical conduction. So I have one more example. Stainless steel. The word says it that it's stainless, it's not stain-free. So when people use the stainless, and Professor Eager talked about it, I believe this in this module, so I'm going to focus more on what to do when it happens. So you have stainless steel that's used and it's starting to pit this way, and it's because of high chlorine normally on the surface. So one way to do it, this is a special architectural situation. We prepared it one way and subjected to accelerated corrosion, and then we did it another way. So this was just refinished, and this was refinished, and then we put a small lacquer on the surface, nothing sophisticated, just a very, very mild lacquer. And the only difference is adding a very, very compliant, transparent lacquer on the surface protects you against the big salt iron. So the salt irons can't go through the lacquer, and therefore now you don't have this high chlorine environment, and you're not going to be pitting. So the concept of having the moisture penetrating in the case of stainless steel is not a problem. Oxygen is not a problem. All you needed to do is that lacquer to hold the irons. And so it's used for bolts, ships, and the different like nice looking structures that you can just with a solvent you can remove that lacquer. So let's say you're going through maintenance, you strip it all off, and then you come and put another layer on before it goes to service again. But we're not talking about super long life. It's not very thick, but it doesn't change the appearance too much. The reason why it's dull here is this something they wanted. They wanted a dull finish. It actually didn't help because they were blasting the surface and creating little holes or sites for the corrosion to start. The pitting to start. So we reproduced the finish that they were looking for. So this all worked, but it wasn't an easy process to re-prepare the corroded surface on site. So a lot of times you wish you had done it right the first time and taken everything into account. So for corrosion, it depends which metal you're looking at, right? So when we were talking about steel, we said we don't want to have moisture. If we talk about stainless steel, we don't want the chlorides. If it's aluminum, we don't want it super acidic or super basic. But all I say is that there is a lot of information, and the ASMN books, volume 13, they broke it down into 3 different volumes. Has a lot of easy information, so if you're trying to learn about one in particular, you can go there, and they give plenty of examples on why you use certain things and why you don't use other things. If you're talking about temperature exposure, everything becomes a different situation. So a lot of stainless steels are going to become at risk for stress cracking at elevated temperature. So if you're thinking, okay, well, this is a piece of stainless steel for a boat or a sailboat or anything like that, then that's fine. But if it's a pressure vessel for chemical processing, a lot of times it's surprising that they have to switch back to regular steel and handle the fact that it's going to corrode, to lose section, just so they don't have these brittle cracks, the stress corrosion taking place and then having failures related to that. So they call it corrosion control. When I was taking classes, it's because you can't completely avoid it, and the most you can do is control it. That's what I had. Thank you.